this is the last topic from previous class. So we talked about type 1 error and type 2 error. After we left the class, I thought of a better example. I remember I gave an example whether this person has stroke or not and what the doctor diagnoses, right? So to be more in line, with this slide, I think this example would be a better one, right? So let's say we say that the null hypothesis is that somebody doesn't have COVID, right? So the patient doesn't have COVID, right? Quite similar to the example that I have, but we want to frame it similar to hypothesis testing so that, we can relate type 1 and type 2 errors, to what we have in this chapter. So the patient doesn't, or actually, say the patient does have COVID, right? And then the alternative hypothesis would be doesn't have, right? And then we have a table similar to before, right? So here we will have either H0 is correct or it's wrong, right? And in either case, the diagnosis can be two. The diagnosis can either be, so here I'm going to write down the diagnosis, maybe with another color. Right? So the diagnosis can be either has COVID or doesn't, right? Right? So if the patient has COVID, and the diagnosis also says that, you have COVID, then this is basically, these two are correct classifications, right? We say that, the patient has COVID and the diagnosis is also that, the person has COVID. Or the person doesn't have COVID and the diagnosis also say that the person doesn't have COVID, right? So these two are the good things that we want to maximize, right? So basically we want the probability of these two to be 1, right? And then these other two are the bad ones that we try to minimize, right? So this one is type 1 error, type 1 error, and this one is type 2 error. Right? I think this is easier to understand. Any questions? Yeah.
I'm wondering how come the lower part of the chart has type 1 and then the upper part of the chart has type 2? Was that just simply they chose that order to make?
Yeah, that's a good question. So perhaps because this was column 1 and this is column 2, they prioritize column 1 to column 2, right? And the other reason could be that type 1 error is easier to calculate than type 2. We will see that type 1 is much easier. And first we talk about type 1, and then we talk about type 2. Yeah, that's a good question. I thought about that too.
Okay, thank you.
Yeah, sure. Any questions? Okay. So type 1 error is also called alpha, right? And type 2 error is also called beta. And another thing that we will see, so in this book, in this chapter, later on, we talk about something else called Pvalue. But Pvalue is essentially the same thing as alpha, right? So alpha is basically Pvalue. The book doesn't say that alpha is the same thing as Pvalue, but later on when we talk about it, Pvalue is the same thing as alpha, right? So Pvalue is the type 1 error that we estimate. So this is Pvalue is for later. We'll talk about it later. So if we go back to the slide, let's try to visualize these errors with normal distributions, right? So for type 1 error, right? So alpha, we basically are saying that H0 is correct. That means that, so for alpha, we are saying that H0 is correct, right? So that means that the true distribution mean is here, right? So the true distribution mean is, for example, mu 0. And then what we calculate is the probability that we get so unlucky and all of the samples that we select are far from mu 0. And then the final mean that, for example, is x bar, ends up somewhere here, right? It is possible that we have a distribution like this, as I showed, and let's say we take few samples. Let's say we take only 3 samples. It's quite possible that the average of those 3 samples, is x bar that I have shown, far from the actual mean, right? So, as I said, as we said in the previous class, we usually have a decision boundary, right? So we say that, if this is your null hypothesis, that mu is this guy. If you're further from mu than, some boundary, then you say that I'm going to reject the null hypothesis, meaning that the null hypothesis is correct. Null hypothesis is incorrect, right? So here, basically, what we are interested in is the probability. So let's say this is that basically boundary, right? So in the previous slide, this boundary was from 48.5, right, to 51.5, right? And mu 0 was 50, right? So type 1 error means the probability that you are unlucky and your x bar happens somewhere here. And the probability of that is the area that I have colored in purple, right? So we can actually calculate, with tools that we learned from chapter 4, we can calculate the probability of the shaded area, right? So we already know type 1 error, how to calculate type 1 error. Any questions? So basically in this chapter, we will solve questions exactly similar to this. We want to calculate the area, under the curve, in the colored area. And that's called alpha, and that's also called p-value. They're all the same thing. And then for type 2 error, we are saying that H0 is false, right? So that means that if this is my so this is, if null hypothesis is correct, so this is mu 0, right? Assuming that the actual distribution has a mean of mu 0, right? But here we are saying that the null hypothesis is false, meaning that mu is actually not mu 0, it's some other value, right? To calculate type 2 error, we have to somehow guess, or the question has to tell us what is the other mean, right? So the actual mean is this other guy. So this is, for example, mu 0 plus delta, right? It's away from mu 0 by a little bit, right? So perhaps here it was better to, so I didn't think ahead about my color choices. So perhaps it's better to show this area in, in green here. And then I can use green here again, the same color, right? So now I had some basically boundary that I would say I would reject the null hypothesis, right? So if from the previous slide, for example, if the x bar that we calculate is between 48.5 and 51.5, we would accept the null hypothesis, right? So this is the acceptance range. Right? So don't worry about how we calculate it. This is really the easy part, how we calculate this range. The more difficult part is the intuition behind these two curves. That's basically the essence of type 1 error and type 2 error. This range is easy to compute. Right? So remember what's the definition of type 2 error? Type 2 error, we say that we fail to reject H0 when H0 is false, right? So when do we fail to reject H0? In the middle, right? This is where we fail to reject H0. So we basically have to calculate the probability that we are in the acceptance range by mistake. And that probability is this area under the curve. Under the purple curve. Because now we are assuming that the actual mean is some mu plus delta. Yep.
Wouldn't it be also the part of the blue curve that is inside the purple?
Say it again.
Wouldn't it be also the part of the blue curve that is inside the purple? Like,
Oh, this part? You mean this part?
yes.
Right? No. So basically, yeah, so the question is, doesn't type 2 error include this area under the blue curve? Right? So that's a very good question, right? To answer that, I will explain again what is type 2 error, right? So type 2 error means that our correct distribution is not the blue line, right? So for now, just look at the top curve here, forget about this curve because we are talking about type 2 error, right? So first of all, H0 is false, and that means that my distribution doesn't follow this blue curve, right? So the actual population, right? Let's say you're sampling from, like a new product that's being manufactured, right? And the mean weight of that product is not mu0. It's mu0 plus some delta, right? So your sampling is going to be from this curve, from the purple curve, because this is the truth, right? The other curve is not the truth, right? What is the importance of the other curve? Other curves comes from the null hypothesis, H0, right? So other curves basically says that I think that my distribution has a mean of mu0, but in reality, my distribution has a mean of mu0 plus delta, right? So what is the use of this blue curve? The use of this blue curve is that since my null hypothesis is that my data comes from a distribution with a mean of mu0, my acceptance range is going to be around mu0. So let's say magically I compute this range, right? This magically is quite easy, right? In fact, you already know that based on chapter 4 material, right? But we will talk about it later on. So we basically find some range around mu0. So in this case, this length is 1.5. So 1.5 before mu0 and 1.5 after mu0, right? And we say that if the X bar that you sample happens to be here in this range, then you actually fail to reject H0 because your X bar is close to null hypothesis, right? What is the probability of that? The probability of that is actually here, right? So basically the yellow area that you mentioned, let's say here, in fact, if your X bar is here, for example, then you're rejecting the null hypothesis because it's like this point is outside of the acceptance range, right? So if your X bar happens to be like here, and by the way, remember that you sample from the purple distribution, not from the blue distribution, because the blue distribution is not the reality. Blue distribution is what I think is the reality, which is wrong, right? So remember that here, I'm stating that H0 is false, and it means that mu is not mu0. It's some other mu, right? And that other mu is mu0 plus delta, right? So if you actually sample here, that's a good thing. So if your X bar is here, that's a good thing because it's outside of this acceptance range here, right? And that means that you are actually rejecting. So you're actually, if if you're doing this, if your X bar is here, then you are here, which is a good thing. There's no error. Did I answer your question? Yeah, so don't worry if, so these two curves is the rest of this course. There's nothing new other than these two, right? So the entire rest of this chapter about these two. So don't worry if you find this confusing. We are going to do, many examples, calculating type 1 and type 2 errors. So now you see the end of the tunnel. There's, other than type 1 and type 2 errors, there's nothing else in this course. Any other questions? Yeah.
The purple shape is a given?
Yeah, so the question should give us the purple shape. Yeah, that's a good question. That's one of the reasons calculating type 2 error is more difficult, because we need additional information, right? Yeah, otherwise we can't calculate the type 2 error. Any other questions? Okay. So let's look at one example. So suppose that the standard deviation of the population is 2.5, right? So this is sigma, and sample size is 10, right? So we have selected 10 samples from some distribution that has a sigma of 2.5. And we want to calculate the probability of type 1 error if this is our acceptance range, right? So let's say, somebody in the company has decided that if you're between 48.5 and 51.5, you're close to mu, so you don't reject the null hypothesis, right? And if you're outside of this range, you reject the null hypothesis. And by the way, here we say we fail to reject H0. We don't say we reject H0, because we don't want to deal with, so if I go back to this curve here, so if, if my X bar is somewhere here, so if this is 48.5 and this is 51.5, right? If my X bar is somewhere here, I'm actually here. I'm in this row, meaning that I have failed to reject H0. Why do I say fail to reject instead of saying that, oh, H0 is true? The reason is that if I fail to reject H0, I don't know whether I failed to reject it because H0 is true or because I made a mistake and I didn't reject it, right? So that's why we say we failed to reject it. We don't say H0 is true, right? So I will repeat again. If X bar happens to be in that range that we accept, right? That means that, either we have, either actually H0 is true and, we are here, which is good. But another possibility is that H0 was actually false, but I thought that I didn't realize that it's false. And I suffered from type 2 error, right? And that's why in the middle, we call this fail to reject. We don't say H0 is correct, right? So there's so many new concepts here. Don't worry if you don't understand. By the end of this chapter, when we solve many questions, hopefully things will start to make sense. Yeah?
Can you say again some reasons why H0 might be false?
H0 might be false?
No, like H0 might be false, even if you fail to reject H0.
Yeah. So here, for example, right? So assume that, so in the top graph that you see here, right? So assume that this is your actual mean, right? Let's say your mu0 was, for example, 50, and assume that this is 52, right? So assume that the mean of your population is 52, right? But assume that you sampled only 3 samples from this population with a mean of 52, right? When you sample only 3 samples, it's quite likely that your average is somewhere here, right? If your average is here, then you suffer from type 2 error, meaning that your actual mean was, 52, but by chance, the few samples that you selected are around here, right? So that's the case that, you know, your X bar is here, but your actual mu is somewhere else, right? Any other questions? Okay. All right. So let's go back to the question. So standard deviation of the population is 2.5 and sample size is 10. Right. We want to compute the probability of type 1 error, meaning that we basically reject the null hypothesis by mistake, right? What does that mean? That means that, let me see what color I showed that guy. So blue, right? So that means that my true mean is somewhere here, right? So this is my true mean. So this is actually my population, right? But by chance, I'm very unlucky, and my X bar either happens here or it happens here, right? And I think that, oh, the mean is actually not 50. The mean is, something else, right? So I guess now you can guess what's the rest of the solution. All we have to do is to calculate this area plus this area, right, under the curve. And for that, we need the material from chapter 4, right? So basically, all we have to do is that we have to convert this distribution with a mean of 50 to something that's standard normal, right? And we remember the transformation for that. It was 48.5 minus mean divided by 2.5 divided by square root of 10, right? That's it. So we solved the question. So this is Z. Can somebody please punch it in to a calculator?
Minus 1.89.
Thank you. 1.89? Yeah, that's fine, 1.89. So this is going to be minus 1.89, right? So that means that 48.5 is going to be transformed to 1.89. And similarly, the other guy is going to be transformed to plus 1.89, right? And basically, all we are interested in is this area under the curve. And for that, we look at the table, right? We look at the table for 1.89.
Sorry, could we get just one side and double it?
That's what we can do for sure. Yeah. So you calculate one of the areas. So you look at the table for 1.89, and you say that this other area is exactly the same as this area. So these two, colored areas are the same. So whatever you get for 1.89, you double that. Yeah. And you can do that for, for normal distribution and for T distribution, because T distribution is also symmetric. But you can't do that for chi-squared, because chi-squared is not symmetric. Any questions? Is there anybody who wants, basically, half of the rest of this course is about this, right? And the other half is about type 2 error. Okay. So basically, according to so this is the same solution that we did. According to the central limit theorem, X bar has a normal distribution with a mean of 50 and standard deviation of 2.5 divided by square root of 10, which is 0.79. So so it was, the correct value was 1.89, right? So this is quite close. So we calculate these Z values. and then we look at the table, Z of less than 1.9, and then this value from the table is 0.028, and the other area is exactly the same, so it's 2 times this area. So that means that if mu is 50, there's a 5.7% chance that all random samples would lead to rejection of the null hypothesis if the null hypothesis is actually correct. Right? Yeah.
You say all random samples, but then we just sample 10.
Yeah, so by all random samples, yeah, that's a good question. So all random samples of size 10. Yeah, that's a very good point. Right. So that means that if you sample 10, right, and you repeat, you sample 10, 100 times, in 5 times out of those 100 times, you reject the null hypothesis by mistake.
And the lower the sample size, then the higher the...
Exactly, yes, exactly. That's a very good point. So if we go back here, so basically the blue curve that I drew is for, remember that, here, the standard deviation of X bar is this guy here, right? 2.5 divided by square root of 10, right? So that means that if instead of 10 samples, for example, I had, so if I change 10 to, so let's say with a different color, let's say with purple. So if instead of 10 samples, I had 5 samples, and I calculated X bar, so X bar is calculated with 5 samples, right? So that means that, so the blue curve that I drew here is for if we have 10 samples. Now if I have 5 samples, my normal distribution has heavier tails. So it means that it's going to be something like this. Right? So this is, again, the distribution of X bar, but with only 5 samples. And that means that this area under the curve is much bigger than before, right? So there is a more chance of error, right? And that does make sense intuitively. If we have fewer samples, there's a higher chance that we reject the null hypothesis even when the null hypothesis is correct. Any questions? Okay. Okay, so next part asks, what if alpha of the acceptance range was changed from 48 to 52, right? So in the previous slide, what we looked at was, oh, what happened to my writings? Okay. So here, we investigated what would happen if I have 5 samples instead of 10 samples, right? The next part of the question is asking what happens if you change the acceptance rate, right? So instead of 48.5, what happens if your range increases to from 48 to 52, right? So basically, you reject the null hypothesis if you're here or if you're here, right? So with basically this new range, does alpha increase or alpha decreases? Yeah, it decreases, right? Because compare the 2 areas, right? The new area is much smaller than the previous area, right? So if we increase the range, then probability of making an error is smaller, right? So we can actually calculate that. So here we calculated Z for 48.5. We can repeat the same procedure. Instead of 48.5, we can calculate Z for 48, right? And we get a number here, new number here, and we look at, so instead of 1.89, we are going to get a smaller number, probably like -2 or something like that, right? And if we calculate, I think the answer is here. So if we calculate the answer is 1% only, right? So the probability of error decreases from 5% to 1% if we increase the range. Yeah. Yeah, okay. Okay, so basically in the previous part, my acceptance range was from, so the computation here that we did, right? The computation that we did here, we computed Z, so we basically converted this blue curve here into this new blue curve by this transformation, right? And this transformation is basically what we studied in the previous chapter. Basically it says x bar minus mu divided by sigma divided by square root of n is a standard normal distribution, right? So now the question is asking, yeah, so I think I need this is too cluttered. So let's add a new. Okay. So I computed the probability of type 1 error. So 48.5 and then 51.5. I calculated the probability of type 1 error in this case, which was this area under the curve, right? Now the question is asking, what if your acceptance range has changed and now the new acceptance range is the following? So it's the same thing. This is 50, this is also 50, but here your range is from 48 to 52, right? It means that now I'm interested in this area under the curve, not on the previous area under the curve. Again, I recap why we are interested in this area. The reason that we are interested in this area is that we are assuming that our correct mean is 50, right? So we are looking at the product that has a normal distribution with actual mean of 50, right? But we are unlucky, right? And when we sample, by chance, our sample mean happens to be here. And that's quite possible, right? If you only sample 3 or 5 or 7 or 6, right? If you have few samples, it's quite possible that all of them are smaller than the mean. And at the end, you get an X bar that's here, right? What does that mean? That means that you're unlucky and you select a few samples that give you, for example, an X bar of 47, right? And you say, oh, X bar was 47, so I reject the null hypothesis. Mean is not 50. Why? Because my acceptance range, so the question says that sets your acceptance range to this range. And if your X bar is outside of this range, that means that you're rejecting the null hypothesis, right? So if you're here or here, you're rejecting the null hypothesis, right? So all we have to do is to calculate this area under the curve. And for that, I have to use basically this transformation that Z is equal to 48 minus 50 divided by, I guess, 10, 2.5 divided by square root of 10. Thank you. Right? And can you calculate this one, please?
Minus 12.63.
Minus 12? I don't think so.
Oh, minus 48, sorry. So minus 2.50.
Yeah, that makes sense. So can you say that again? Minus 2?
0.53.
And the other guy was, oh, what happened to the other guy? Huh. We lost all of our,
Minus 1.9.
that's weird. Yeah, we lost all of our, yeah, because okay, I see what's going on. So what was the other one?
Minus 1.90.
Right? So basically now we are looking at, with the new boundary of 48, we are looking at phi of minus 2.53. Previously, we were looking at phi of minus 1.92, right? And that phi was, what was this?
6%.
This guy, right? 0.028. So this guy was 0.0287. And did you say, did you look at this one on the table?
Oh, I know the table.
No? Yeah, so this one from the table is going to be, since the question already gives us the answer, this guy is going to be this divided by 2 if you look at the table. So if we look at the table, right, for minus 2.53, the answer is going to be that the final answer divided by 2. Right. So in the case of the green curve, alpha is going to be 0.01 or 1% chance of rejecting H0 by mistake. And in the blue curve, alpha was 0.05 something, 57 I guess, or 5.7%. Right? So that means that if my rejection range is from 48.5 to 51.5, there's a 5% chance that I reject null hypothesis by mistake. And if my rejection range is more strict, meaning that instead of 48.5, it has to be either smaller than 48 or larger than 52, then my alpha is going to be 1%, much smaller. And that does make sense, right? Because in the second case, I'm more strict, right? I'm saying that, oh, it has to be, less than 48 or more than 52. Any questions? Okay. Right. So don't worry if you think that you haven't understood type 1 error again, because we come back to it in the form of p-value. And p-value is the same thing as the type 1 error, right? So we will calculate a lot of type 1 errors later on, right? But let's look at what is type 2 error now, right? So we sort of understand what's type 1 error. Let's try to understand what's type 2 error. So as we said before, when we calculate type 2 error, we have to assume, or the question has to basically tell us what is the true mean, right? So here, the true mean is 52. So that means that this is actually my population, right? My population has a mean of 52, right? Because the question says mu is 52, right? But my null hypothesis says that mu is 50, right? And based on that, I have calculated this range between 48.5 and 51.5. So this range is here, 48.5 and 51.5. right? So yeah, I didn't hear as many alarms as I expected. Yeah, I know this was just a test, but guess everybody's cell phone is on airplane. So this was there was a test. No, I think I only heard your phone.
Maybe someone added to, it's Amber Alert.
Yeah, Amber Alert. Yeah, but only I heard one phone that rang that. Oh yeah, okay. Yeah, you guys are good. So basically, we are interested in this area under the curve, right? So that's type 2 error. So basically, I will repeat, what is going on. So my product has an average weight of 52, right? The average weight of my product is 52 grams. But, my null hypothesis is that the product has a mean of 50 grams, which is incorrect, right? The actual mean is 52, right? And somehow I have selected this to be the range that I accept or reject the null hypothesis. Again, don't worry about how we select, like where do these numbers come from. They are around the mean. They are around 50, but we will see how we calculate this range, right? So basically we have set up the question as before. So if I go back to the very first slide here, I have set up the question as follows. I'm saying that if X bar is here, I do not reject H0. If H bar is here, I reject H0, right? Now for type 2 error, what I'm calculating is what's the chance that so basically what I'm calculating is the chance that X bar is here by mistake when mu is actually 52, right? This is what I'm calculating. So I'm calculating the probability that X bar happens to be here, but by mistake, the actual mu is 52. And this is type 2 error. Beta, yeah.
So I understand so we know that the mean is 52, so why do we choose, what's your hypothesis?
Yeah, so that's a very good question. So no, mean is not, actually we don't know that mean is 52, right? So let's say that, so this is basically one of the weaknesses. Like in real life, when you want to calculate type 1 error, you can simply calculate it, right? But with type 2 error, you have to somehow, assume, like of course you don't know what mu is. If you knew what mu is, then there's no need to actually do tests, right? So what you actually calculate here is sort of like, so we call this the power of the test, right? We say that how powerful our test is, meaning that, if the actual mu was 52, it can basically find out that, null hypothesis is correct. But if the actual mean, for example, was 50.1, right? That's very hard to reject the null hypothesis if the actual mean was 50.1, right? So it's sort of, so like I said, we will see later on, beta, 1 minus beta is called the power of the test, right? So we want higher power, right? And power basically means that, how different your true mean can be from the one you assume that you can actually still distinguish that it's actually a different mean, right? So for example, if your actual mean is 52, right? That means that probably with 20 samples, you can find out that null hypothesis is incorrect, right? But assume that instead of 52, so here in this case, so we will talk about this later on. We will calculate n, like how many samples you need based on, this 52, right? But since your question is a very good one, I like to answer it now. So from this, we can say that, let's say we will see that, for example, with n equal to 10, we get reasonably small beta, right? But let's say that your mu is actually not 52. Your actual mu is 51, right? Or like 51 point, it has to be outside of this range. Actually, it doesn't need to be, so it can be 51, right? So let's say your actual mu is 51, right? So now how many, actually no, if it's inside this range, then it doesn't work. So it has to be, for example, 51. So this is your acceptance range, right? So let's say your actual mu instead of 52 is 51.6, right? Just a little bit outside of this range, right? Now, how many samples do you need to be reasonably sure that you can reject the null hypothesis? In this case, if you calculate n, you're going to get a much larger n. For example, instead of 10, you probably are going to get n equal to 100, right? So your question is, how do I know mu is 52? We don't know what mu is. We say that, how many samples do I need such that for a mu of 52, I have a reasonable power, right? I think that's the best way to answer it. Okay. So basically my mu is 52, right? So this is the true mean, that's unknown, right? And my null hypothesis was that mu is 50, right? And I want to calculate the probability of type 2 error. So basically all I have to do again is use the same equation as before, x bar minus mu divided by sigma divided by square root of n, right? So if we do that, then this distribution becomes the following distribution in the standard form. So this is now 0. 51 becomes minus 0.63. And then 48.5 becomes minus 4.4. Right? So the table, I think the table doesn't have numbers smaller than minus 4, right? And there's a reason for that, because those numbers are pretty much 0, right? So this is 0, right? This is 0. And then for 63, we get 0.26, right? So that means that the probability that we fail to reject the false null hypothesis is 26%, a relatively large probability. Yeah.
So like when you shift the 52, you said it could be at 51.5. Could it be less than 51.5?
Yeah. So I mean, so the range. We will talk about how we find the range. This range comes from alpha, right? So let's say somehow we have locked this range, right? So this range is fixed. It's between 48.5 and 51.5. So if this is the range, then if the actual mean is less than 51.5, then we cannot actually find out that it's a different distribution, right? So the actual mean has to be more than this guy or less than this guy. Has to be outside of this range. So basically now we have a large, a very large chance that we fail to reject the null hypothesis, even though the null hypothesis is, is incorrect, right? So, so for example, one thing that, we can think about, and this is what we will do later on, is that, this doesn't conform with our, with our standards, right? So let's say this probability is too high, right? We don't want 26%. We want, for example, 10%, right? So basically, we want to decrease this number to 10%. 0.1, right? So that means that when the true mean is 52, we want only in 10% of times our X bar to be here, around 50 by mistake, not in 26% of the times, right? So what practical way can you think of that we can do this to decrease, this beta, the probability of type 2 error from 26% to 10%? What is it? Yeah, you can reduce the range. Yeah, that's one solution. Yeah, so you can reduce this range for sure. Is there any other way we can do this? Yeah, so when we reduce the range, the probability also becomes smaller. Yeah.
Increase the sample size?
Yeah, we can increase the sample size, exactly. So if you want, your probability of type 2 error to be 0.1, that means that you have to increase your n, So what was n here? I think n was 10, right? So let's say if you increase your 10 to, 30, so make it 3 times bigger, then your new distribution is going to look something like this, right? And because of that, the new area under the curve will be only 10% instead of, 26%. Right? So we will talk about this later on, right? How to calculate n from beta. Any questions? So I'm actually not sure the answer is 30. It's basically a number larger than 10. Right? We will see the equation for that. Okay. So 1 minus beta is called the power of a test, right? So beta was probability of an error, right? So we want beta to be small. So 1 minus beta is power, and usually we want power to be high, right? So beta is probability of correctly rejecting the false null hypothesis. Right? So this is actually a mouthful. Rejecting false null hypothesis, right? So many negatives added up to each other, right? So you have to really focus to basically, make sense of what does this basically phrase mean. It basically means that H0, where, for example, we assumed mu equal to 50, is wrong, right? In other words, mu is, for example, 52, right? And power is basically 1 minus beta is the probability of rejecting H0, right? So power is the probability of rejecting H0 when H0 is actually wrong. Okay. So in the same example that we did before, H0 is mu is 50, and H1 is mu is not equal to 50, right? Suppose that the true value of the mean is 52, and suppose that we have n samples, and basically same story that we had. We calculated X bar, so we just found that beta is 0.26, right? So that means that power is 1 minus 0.26, which is 73%, right? So that means that we will correctly reject H0 in 74% of the times. And that's usually not a very large power. We usually want like a 90% power, right? 70% is not considered very high. Any questions? Okay. So as I said before, P-value is another parameter that we are interested in calculating, right? So, you know, your book actually doesn't mention that P-value is the same thing as alpha, and that's something that I don't like, you know, about the book. It is the same thing as type 1 error, right? Probably the reason is that there are so many different, you know, conventions for, you know, for statistical testing. So like a lot of people use p-value. P-value is the phrase that's most commonly used, right? Not alpha, right? But anyways, p-value is exactly the same thing as alpha, and as I just said, it's very, very commonly used, right? So everybody refers to, like, if everybody wants p-value when you do a test, right? And as I said, is the same thing as alpha, probability of type 1 error. And it's also called the observed significance of a test, right? So if you write a technical, you know, report, then the word significant, you know, has a meaning, right? So if you just say that, oh, we see significantly different results, right? Just because you looked at the results and they look very different, right? So you use the word significant in its English, for its English meaning, right? Many people may object that, right? Because significant has a dedicated meaning, right? And significant means that it has a very small p-value, right? So the convention is that when you say significant, you have actually calculated the p-value, and the p-value is small. Okay? So a lot of times when we write papers, we haven't calculated p-value, we don't use the word significant. We use substantial or another word, right? Because significant has meanings, right? And the p-value has to be smaller than, so this is a convention. When p-value is smaller than 0.05, we say that our results are significant, right? So that means that the probability of, you know, rejecting the null hypothesis by mistake is only 5%. Any questions? Okay. So let's basically look at an example. So let H0 be 50 against H1 that's not 50, right? And let's say we have 16 samples, and the standard deviation of the population is 2.5, and suppose that the observed sample mean is 51.3. Should we reject the null hypothesis, right? So, you know, from 16 samples, we have calculated a mean of 51.3. So in other words, what's the probability that a sample mean of 51.3 is observed if the true mean is actually 50, right? So the true mean is 50, right? And we want to calculate the chance that, you know, the X bar that we calculate is as far from 50 as 51.3, right? So we want this area under the curve, right? But, you know, since the question doesn't say that, you know, it's a one-sided test, meaning that it doesn't say that, oh, we are only interested if it's more than 50, we have to also look at the other side. So we have to subtract 1.3 from 50. So that's going to be 48.7, right? So basically, we have to calculate this area under the curve, right? This area plus this area. So again, I will summarize the question. We have calculated some, you know, sample mean. The sample mean is 51.3. We want to find out what's the probability that the sample mean of 51.3 is observed if the actual true population mean is 50, right? So if the sample mean happened to be 51.3, meaning that 1.3 more than the actual mean, it could also be 1.3 less than the actual mean, right? So we should look at this area as well. And you probably have guessed the rest of the solution. We have to make this into standard form, right? So again, we have to use the equation z is equal to x bar minus mu divided by sigma divided by square root of it, right? So this becomes 48.7 minus 50 divided by 2.5 divided by square root of 50, right? And that's it. We have z, and from z we calculate phi, and we multiply that by 2. Okay, so let's continue. So, yeah, so as I said, we are looking at either 51.3 or, in the other extreme case, 48.7. And we basically want to calculate this area under the curve, the summation of these two guys, right? So the z that we get from this computation is minus 2.08. So from the table, minus 2.08 is here. So it's 0.018. So this area under the curve, so this area is 0.018. 7, right? This area. And then the final answer, p-value, is the summation of these two. So this times 2 is the p-value. And that's 0.038. So this is the same thing as alpha, probability of type 1 error. Any questions? So if H0 is if H0 is true, the probability of obtaining a random sample whose mean is as large as 51.3 or as small as 48.7 is 0.038, right? And since this number is less than the convention, so the convention is 0.05, right? Since this is smaller than 0.05, therefore we can reject H0. Any questions? So meaning that the mean is actually not 50. The mean is either more than 50 or less than 50. With a significance of 0.038, right? Or around 4%. Questions? Okay. So we talked about, looking at a hypothesis and finding whether a hypothesis is correct or not, and that usually helps us make decisions, right? So I found this article quite interesting. So basically, what happens is that our cognitive bias, when we want to make decisions, usually makes suboptimal decisions, right? And that because one of the main reasons for that is that we are against change, right? So we are basically always for status quo. We like status quo, even though if the other option might be better, right? So there's something in our cognition that always inhibits, making good decisions. And basically what this article looks at, and it's based on, research in economy, they basically say that if you want to make big life decisions that are very important, right? And the two options, seem about equal, the best way to make a decision is to flip a coin. Because if you decide, then since you're against, change, you always end up with status quo, which is very often not, the best decision that you can make. Right? So I found it quite interesting that, basically, often we don't make rational decisions, right? We make wrong decisions. Okay. So I guess that's it for today. Next class, we talk about the rest of, type 1 and type 2 errors.